All right. Thank you, Cliff. Hello, everyone. Very happy to be here and to talk. This way. Okay, this way. It's good. Can everyone hear me? Okay.
Yes.
Okay. All right. Yeah. So I'm very happy to be here today to talk about quantum computing and to talk about our joint approach with Equinix. So I'm Laurent Prost. I'm product manager at Alice & Bob. We're building a fault-tolerant quantum computer.
And hi everyone, lovely to join you today. My name is Petrina Steele and I represent Equinix for AI, quantum and edge strategy.
Okay, so we're working together on bringing quantum computing to companies around the world and Equinix customers in particular. And I would like just to say a few words about quantum computing in general. This is particularly interesting because we don't get so many opportunities to engage with people who are not in the quantum computing world. We do a lot of quantum computing conferences. And there are different fields that will be affected by quantum computing, some more than others. We expect that the first applications are going to be probably in chemistry and in material science, but there are also other applications that are going to come later in cryptography, in finance, and in other domains. As I think you understand, quantum computing is more of a long-term bet. When we're looking at the reports by consulting companies, they estimate that the impact, although it's going to be massive, it's going to be in hundreds of millions of dollars and possibly even trillions, is going to happen probably, it's going to start happening probably by the end of the decade and by 2035 for some maximum impact. And I would like you to understand why this is the case, because one remark that we often get is, okay, but quantum computing is a long time in the future, why do we need to care about it now? I would like you to understand the fundamental difference between classical computing and quantum computing. So when we're working in classical computing, we're using bits, zeros and ones. I don't think I'm teaching you anything here. And when you have n bits, then you have a longer string and you can store more data, but so one more bit is just one more bit of information. But with qubits, things are different because a qubit uses the properties of quantum physics, and the state of a qubit can be described by two coefficients, as you can see here, and each coefficient corresponds to 0 and 1, and so you have the properties of the 0 and the properties of the 1 at the same time. So this is a potential for parallelization of computations, and when you have n qubits, then you really realize this potential because you have all 2 to the n string bit combinations that are possible, and you have a coefficient associated with each of these combinations. And so people usually say that when you have n qubits, then you can do 2 to the n computations in parallel, and so it makes quantum computers much more powerful than classical computers. Unfortunately, this is not the whole story. This principle alone does not work. And I would like to give you an intuition as to why this is the case. And so if we look at, for example, a factoring example, so you want to factor a 4-bit number. So there are two possible prime factors. There are 2 and 3. If none of them is a factor, then of course your number is prime, and otherwise then you found a way to factor your number. So simple algorithm, you check whether 2 is a factor, 3 is a factor, and then based on these two answers, then you have the answer to your problem. You can, of course, parallelize this by using, for example, 2 separate threads, one that is going to compute the division by 2, one that is going to compute the division by 3, and then you speed up your whole process, and then, of course, when you work with bigger numbers, the more cores you have, and then the faster this is going to be. And you could think that, okay, because quantum computing is super good at parallelizing things, then when you're going to have to factor a very big number, then you're going to be able to try all possible combinations in parallel, and this is going to be super fast because you only need a logarithmic amount of qubits regarding the size of your number. Unfortunately, this is not the case because when you have a qubit, when you read the state of your qubit, you only get one of the possible states. And what it means is that you're going to get only one of these answers here, and you're not going to get the rest, and you're not even going to know what factor it corresponds to. So this is the reason why, even though parallelization is very important in the advantage that you get from quantum computing, this is not the whole story. You also need to cleverly manipulate the states that you have here in order to maximize the probability of measuring a useful answer. I'm not going to go through the details of how you do this because 20 minutes would not be enough. But I hope that this gives you an intuition as to why quantum computing requires some specific developments and some specific algorithms. And this is not just about using the principles that we have in classical computing and just porting them to a more powerful computer. Second problem that we have is that currently quantum computers are just very bad. If we look at the error rates, the very best computers today are something like 10 to the minus 3, so one error every 1,000 computations. And we estimate that the first useful applications of quantum computing are at something like 10 to the minus 9, which, if you think about it, is already terrible, because a classical computer is probably at something like 10 to the minus 20. But even with just a 10 to the minus 9 target, you see that it's going to take a long time if we just wait for the hardware to get better based on the current progress. And so we need something to go faster. We need something to have more reliable quantum computers. And this is what Alice and Bob is trying to achieve. So Alice and Bob was founded 4 years ago by 2 PhD students who are working on quantum information and on a specific type of quantum bit that we call the cat qubit. And cat qubits are great for error correction, as I'm going to explain right after. So far, we've raised 30 million euros in VC capital, about the same amount in public funding, so from government programs in France and in Europe. And we are now more than 80 employees working on building this quantum computer. The core advantage of the cat qubit technology is that it reduces the number of qubits you're going to need to implement a useful quantum computer. Because, so as you saw, the error rates of quantum computers themselves are declining slowly, are improving slowly, sorry. And the solution for that is to implement quantum error correction to use redundancy to encode information in several qubits in order to preserve it from noise and from errors. But this uses a lot of qubits. As you can see, when you have 2 types of errors to deal with, which is the case of the vast majority of quantum computers, you need to make a grid of qubits, like so, to correct errors, and this requires a lot of physical qubits in order to implement just a single qubit, logical qubit with fewer errors. If you use cat qubits, because cat qubits are inherently protected against one of these 2 types of errors, then you basically remove a dimension and you greatly reduce the number of qubits you're going to need. There are 2 proofs for that. For an experimental proof that we made, where we showed that we're able to reduce the noise in 1 dimension, and we only need 1 qubit to achieve what Google achieves with 49 qubits and the repetition code. And if we look at the long-term perspective, at what it takes to run Shor's algorithm, for example, the Google estimation is 20 million qubits, and we estimate that we can do 100,000. 100,000 is still a lot, but if you take this principle and reduce, you can also apply it to smaller chips, and this makes us expect that we can have something like 100 logical qubits with only 1,500 physical, which is almost doable by the standards of the hardware that can be done today. So at Alice and Bob, because so we are aware of the 2 problems that I mentioned earlier. So of course, the core of our activity is focused on creating the hardware that is going to achieve very low error rates. So this is maybe like 80% of our activity. But we're also aware that there's a need to develop new algorithms and new ways of thinking about solving problems with quantum computers. So this is why we also have a business unit that we call The Box. And that is about working with industrial end users to solve their problems and understand how quantum computing can help them. So a program with The Box usually works in 5 phases, as you can see here. First of all, we're going to go through all the possible use cases of the company. We're going to try to pick one that has a good potential for quantum. And we're going to work on designing an algorithm, estimating the resources of the computer that should be able to run it, and then, of course, try to understand what it takes to actually put this in production. And this is where we're starting to think with Equinix about what it takes to actually have a quantum solution in production and solving problem for customers.
Thank you, Laurent. So for those of you who are not familiar with Equinix today, we're a global digital infrastructure company with over 210 data centers around the world in 71 markets. covering 71 countries, covering 33 markets. We service about 10,000 customers, and a range of those customers are sort of enterprise end users, but also network providers, cloud providers, and also managed system integrators, GSIs, etc. And so when you look at our history, our name means equality in internet. So we were born out of the requirement for internet service providers to be able to peer traffic with one another. And our history is shown over time it's evolved, but effectively we are an enabler for platforms to come into the market on a more scaled perspective. So we started in networks. We then very quickly moved from networks into content providers who needed to exchange content with one another. And then what we found is those content and networks then delivered communities. They delivered communities that were latency sensitive, or they needed data. They need to be able to share data with one another. And so they then built communities together within the four walls of Equinix over those 210 data centers. And so as we kind of extrapolate that forward, we're at the stage now where we're seeing quantum really start to come into the data centers to really look at, well, how can we access real life customers who are interested in trialing quantum? How can we combine those with networks for QKD and for other trials that are there? And how can we actually start to work with some of the GSIs and some of the providers already who are on net that are already resellers across the Equinix platform? So that's sort of why we're working very closely with some of the quantum community today. And so what have we learned? We currently have about 10 providers that are on net at Equinix today, and they're across a variety of different modalities. So the most advanced modalities that we have with us are in superconducting circuits. We also have atom arrays and photonics as well that are with us, and we've learned the following 6 things. So my previous speaker was talking about a lot of these, so I'll be repeating some of the things that he said. But one of the big sort of learnings we had was around really looking at cooling. How do we provision cooling into a typical data center? What kind of soundproofing, electromagnetic shielding do we need to deliver to an already existing, fully multi-tenant data center? So that was one of the big areas. And what are the best practices around that? I think also in terms of installation, some of the I would say supporting infrastructure requires a different view as to how you then bolt those down into concrete floors. So that was one of the big learnings for us. From a space perspective, we also learned that whilst quantum computers can take up a lot of space, they actually don't take up that much power. So in comparison to some of our big sort of X-scale customers, so some of the cloud providers, but also some of the big AI models and that are doing training and simulation, or some of the big enterprise customers that are doing AI modeling or fine-tuning with us, they take up a huge amount of space, a huge amount of power. So the thing there is to really think about loading and accessibility. So the ability for us to be able to bring in the quantum compute sometimes requires a forklift truck to come into the actual data center. The canisters, for example, that are protecting the superconducting circuits, they also are quite heavy. So those are things that normally can't be transported by personnel. So those little nuances for a data center provider are things that we just have to get our heads around. And then our connectivity perspective. So Equinix ourselves, we offer our own sort of layer 3, layer 2 fabric that we built for the hyperscalers to allow them to be able to on-ramp some of their customers and be able to move some of their data very quickly into the cloud. And so when we start talking to quantum providers about the ability for them to connect into established fabrics that are already live, or even some of the networks, that also in itself causes some challenges. So they have to then understand networking, they have to understand what that looks like, and we have to work with them to get through that. And then on a security perspective, as you can understand, huge amounts of security, very similar to some of our government and federal and defense customers, and also our financial customers. Our quantum providers very much look at how they can ensure security around their environment, how they can measure the temperature, and how they can ensure that there is only biometric access, for example, for their space. And then compatibility. This is a big one we referenced probably earlier, which is, again, you have in a multi-tenant data center all different types of customers, some running very large HPC environments, some running GPU as a service providers, and then you put a quantum compute in the mix of that, and that is very sensitive to noise. So that's also a consideration of how we configure some of these tenants together. And then the last point is around ecosystem access. So the ability then, as soon as you get into a multi-tenant data center, the ability then to very quickly connect into networks, into NSPs, into VARs, into clouds, both hyperscaler and local, become really compelling for them to be able to scale very quickly and try out some real-world use cases. So just in terms of what we've been working on with Alice and Bob. So Alice and Bob, for us, our partnership started when they started to look at, is there a way that we can sort of extend our sort of presence into an Equinix data center? So it started off with a metal installation, a bare metal installation, where they extended their virtual IP into our data center. And then from that point, they can then connect into our fabric and then connect to any customer anywhere around the world in those 210 data centers. So you can, whilst they connect in Paris, you can then connect a customer in Tokyo over our own fabric that's there. And then some of our customers are very, I would say, sensitive to their data, and they insist on what we call private AI or private installation. And so this is where they need to be very, very clear on the lineage of data and the ability to have that all in one effectively four-walled location, even if those four walls are in sort of spread out geographically. So here we see the kind of evolution of potentially quantum systems coming into the data center. So Alice and Bob hasn't done this today, but we have a number of other quantum providers. One that we can speak about openly, which is OQC, which has physically put in their quantum computer with us. And then we also have other providers who have worked very closely with HPC integrators that have built and stood up end-to-end QCAS with us as well. So I guess the call to action from our perspective is, as we've kind of heard about today, there's sort of two areas that we see that need standardization. The first one is every single quantum computer that comes in, they have different modalities, they have different requests for how they want to have access for their end customers. There's got to be a way that we figure out what the best practices are and what the standards are for each of those different modalities. And then the second area is around the software area. So again, we talked about agnostic software. Ideally, that would be great to achieve that. But what we're finding with some of our customers is that they are asking for very industry-specific providers. So for an energy perspective, they will want to work with Schlumberger. From a financial perspective, they want to work with NAS, for an example. And so that integration needs to happen. And so we work very closely with our customers to figure out how we're going to be able to do that. So that's just to give you a sense of some of the work that we're doing today. And then if you want to learn anything more, there's a little bit more. We have landing pages. This one's with Alice and Bob, but we have them all for the different quantum providers that are with us, so you can learn a little bit more about what they're doing at Equinix today.
And thank you for
Thank you.
That's great. Thank you.